Hello, everyone. Mr. Hine, and we are now starting chapter 3. Where last chapter we talked about continuity, limits, and this idea of a secant line, which the slope of it represents the average rate of change. Now we're going to be using that to start talking about the average rate of change, but instead of average rate of change, looking at the rate of change at a specific moment, an instantaneous rate of change, what's happening at a particular moment in time rather than a given time interval. So for 311, as we explore this, I know we're not in class. We're in class, it'd be a little bit easier to explore together or in your group. But I'm going to kind of lead you through it. We're going to do number 2 together, talk about some of the concepts here, and that should help you with this assignment. So hopefully you're watching this. Stop, pause it if there's moments where you get a little lost, or maybe you understand it your first time through. So what you see here is the first problem, number 2, and we'll do this together. And we're going to look at the graph of f of x squared. And I'm just going to go through this with you, talk about it as we go. And I'll be going in and out of my paper. So actually, let me do this. Let's see if this works. I'm going to make this half screen. And I'm going to emphasize this button. So we can just look at the problems. Like so. And I'm going to make my paper take on half the screen, maybe 3/4 of the screen, something like that. Okay. So what we see here for the first one is fx squared, and it tells us to graph it accurately and then draw tangent lines at each of those points. So I'm going to do that here. You can maybe skip ahead if you know how to do this. So at -3 be at 9, 3, -2, -1, 0, 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9. -2 be at 4. -1 you'd be at 1, 0, and it's symmetric over the y-axis. Make my curve like so. Okay. Now, it says draw tangent lines in all of them. And just remember for a tangent line means it only intersects one time. Sects once. Unlike a secant line, which we'll be using later, where a secant line intersects twice. Okay. So tangent line means you should draw it where it only hits one time, right? I'll try to do this in red here, and it's not perfect. I'll do my best. So at -3, if you drew a tangent line, now keep in mind the tangent lines would always go on the outside of the curve here, because if it was on the inside of the curve, that actually ended up becoming a secant line where it hits twice. So there's that. At -2, it would look something this up. I messed up there. Slope would look something like that. At -1, I'm going to turn my paper. The slope looks something like that. At 0, the tangent line should be flat. At 1, the tangent line. At 2 again. Oh, that's not done too well. And at 3. So there's small tangent lines at each of those points, and that's A. Now B says use the method that we did in 3.1, which is actually a method that we did back on the worksheet for local linearization and secant lines, to find the slope, the m value, so the m value each of these tables, and we're going to put it in a table. Now for B, I'm going to make a table first so we can see this. M, xm, we're going to find the values at -3, -2, -1, 0, 1, 2, and 3. And remember, the m is the slope at each of these points. Now, there's 3 approaches we can take, and I'm going to show you. Maybe you understand all 3, great. If not, as long as you understand one of them, that's good enough. Approach number 1. The first thing you can do is you can use the idea of a secant line. And how do you secant lines and, secant lines, and I'll put in linear approximation, kind of go hand in hand there. Now, how do you do that is, the idea is, say we looked at -3, if we wanted to find the slope at -3 at that moment in time, and we don't know, well, what we can do is we can look at the slope between 2 points that are just before and just after. So what we can do is we can find the slope between, say, t equals -3.01 and t equals -2.99. Because notice, if we find the slope between these two times, it'll be approximately the same as what the slope will be at -3, right? If you look at a slope between two moments in time, what's happening in the middle there is not going to change much. So this will be an approximation, right? So let's find a slope between these points. So at -3.01, that's the point, -3.01, and then it'd be f of -3.01. This will be the point -2.99 and f of -2.99. Find slope between points, you find the change in y over the change in x. So f of -3.01 be -3.01 squared minus -2.99 squared over the change in x values, like so. All right. And if you use a calculator here, which I'm definitely going to do, you can see that hopefully. So we have -3.01 squared minus -2.99 squared. The numerator gives us 0.12. On the denominator, we add those, you'd be at a difference of -0.02. So if I write that as fractions, that's 12/100ths over -2/100ths. Remember, when dividing fractions, 12/100ths, you flip that to multiplication. And you might be doing this in a calculator, but you can see with fractions, I got an answer of -6. So at -3, the slope is -6 at that point. The slope of this line in red, the tangent line, is -6. And that's one approach you can do. Now I'm going to go through the other approaches, and I'll just kind of show what the answers are. You might be hearing my puppy in the background. He might just have woken up. So I'll try to get to him after this video. All right, approach number 2. And let's see, let's do it over here. So you have the secant lines. The second approach you can use is you can use the Desmos E tool that they provide in the book. All right. So if you look, it's right here. And if I click on this, we'll kind of go through this. And I'm going to make this larger so we can see it for a second. Put the equation in that you want. So we have x to the squared. Click on this arrow here. And now what it does, this Desmos E tool, is it already has the tangent line at each of these points. So say you want to find the tangent line at -3. which I'm just going to do that. Label the point so it pops up. So at -3, it's at 9, and their line hits it once. So what you'll want to do, excuse me, try to show my paper too, is we want to find the slope of that purple line, the slope of the tangent line, right? What's the slope of that tangent line? And remember, for slopes, you need 2 points. So we have the point -3,9. And then we need another point, which, let's zoom in at -2 and see this purple line at -2, might have zoomed in too far, is at 3. So then we also have the point of -2, 3. If I click that, does it show? Oh yeah, it does, see. -2, 3. Okay. So then we find the slope between these 2 points. So let's go back to my paper, which would be 9 minus 3 over -3 minus -2, which will give 6 over -1, which notice we get -6 again, which is just the same we got in approach 1, just a different method. Right? And then we'll look at the last approach, approach number 3. And I know it's not as organized. I would have liked to work downwards, but I want to try and keep this graph on too. And approach 3 is using your graphing calculator, which I actually recommend, because for those taking the AP exam, this is what you will have to use. Recommend if taking the AP exam, I'll just put it that way. But truthfully, you're going to learn a new method soon, which will you'll learn approach 4, which will kind of make this one obsolete. All right, so how do you use a graphing calculator to find the slope at that point? All right, you put the function in, so y equals x squared. Right? And if I graph this, let me graph normally here, y equals x squared, and graph that. All right, there's the parabola. Now to find the tangent line at a point, what you can actually do is use the draw feature, which is right above program in blue. So hit second, program to get to the draw feature. And notice number 5 is you can draw the tangent line. And then you can either pick the point using the arrows, or you can just type the number in. So let's find the tangent line at -3. What it does here is it actually draws the tangent line at -3. You could zoom in if you want to see it up close, but it also tells you the equation of that tangent line, which is -6x minus 9. But all we need for our purposes is the -6, the slope. And notice that that's the third approach. This one, I think, could be a little bit quicker, and there it is. Okay. So there's 3 approaches. Now, I'm not going to go through the approaches for all those tables. I'm just going to fill these in. So then you're at -6. And then at -2, you'll be at, I think, I'm going to just look at my own AMPS queue right away to speed this up and make sure I don't mess up. This is 311, number 2. Okay. So then, yeah, that's what I thought. Just wanted to make sure. At -2, you'd be at -4. Then you'd be at -2, 0. Then you'd be at 2, 4, and 6. All right, so that's the slopes at each of those points. Now, let's go back to the book and see what it's asking next. So we did that. Oh, and then make a graph of f prime of x. So I'm going to try to zoom out because I want you to see a connection I'm trying to make on this problem. So now down here, I make a graph. And we're going to draw what's called the slope function, which the way you label it is f and this little apostrophe almost x. So the slope, this is the slope function. Okay. And at -3, at -6, 1, 2, 3, down 1, 2, 3, 4, 5, 6. -2 at -4, you're at -2, 0, 2, 4, and 6. What you end up getting here is a linear line. And what's the equation of this? So when it comes down to part D, the slope function is linear. And the equation of it here would be y, or we'll use this notation still. Looks like the slope has a rate of change of 2, which you can see from the graph or the table, and it starts at 0, so just 2x. And this is fascinating, by the way, because not only does this relate back to the finite differences that we talked about a few sections ago of how parabolas are now related to lines, but this line right here, if you find the value at any point, you actually know the rate of change of x squared at any point. Notice at x equals 1, at 1, this line's at 2. What that means is that at 1 on this graph, at 1, the slope is 2 at that point. So at 1, the slope is 2. And that's fascinating. So we can just look at a line and figure out the instantaneous rate of change at any given time on x squared. Very useful that we'll be doing soon a lot. Right? So that's number 2. I'm going to zoom in so you can hopefully see this better. We're going to go through a little bit more and then wrap things up on this video. For number 3, if you do number 3 correctly, I'm just going to show you the table. I would love to see some work still. Make sure you still show work so I know that you understand one of these approaches. But what you should get for -3 the negative 3. And this function is x to the third is 12, 3, 0, 3, and 12. And I think if you did the next one, write this down, negative 3, you'd be at 81. No, that's not right. 27. All right. So that's what you should get for the next one. It's okay if you don't do the negative 3. In fact, me, myself, when I first worked through this, I just did negative 2 to 2 to show the rate of change, right? And then again, notice what type of function this is creating when you see something symmetric over 0. And hopefully you can figure that out, what type of function. Okay. Is the slope function. All right. Good. So if we look at the general rule now, which in the next video and section has a name, but the general rule for slope functions of polynomials of degree n. So that's when I say that you're talking x to the first, x to the second, x to the 10th. It's a polynomial of degree n where it can be any power, basically. All right. Sorry about my puppy. I think he really has to use the bathroom. I'm almost done though. All right. So if you have a original function of ax to the n, a polynomial, what we know is that the slope function, which I don't know if I've said, I'm just going to start saying f prime of x is how you actually say that. So the slope function is going to be of the form a times n, and then it's 1 less power, right? Which you can see that's what happened when we did x squared. So when we had x squared, the slope function was represented by 2x. Oh, my darn face is in the way. And hopefully if you do it right, if you have f of x equals x to the third, the slope function will be 3x squared. Okay. And then even the linear one, you'll see what that is, and that should follow suit. So that is very useful to us for now. And we will fine-tune this in the coming weeks. But for now, that's very powerful stuff. All right. Understanding that slope functions represent its own function, and there's a pattern to which they are related. Okay. Now, one more part I'm going to do, and that should help you with all of this. Flip this over because I don't have any more space. So let's talk about the general rule and how it applies for if there's a vertical stretch, if there's a vertical shift, and a horizontal shift. And that should be enough for you to tackle this assignment and understand all the main points. Okay. So the general rule again is that for a given function, polynomial function a times x to the n, we know that the slope function will be f prime of x of a times n x to the n minus 1. Okay. So if we look at a vertical stretch, so say for example, we look at 3x squared. All right. This one kind of follows suit with what we already know, where if we were to compare f of x, let's just do the normal x squared. Well, from our exploration on the first page, we know that x squared, the slope function is 2x. Now a vertical stretch, meaning so if this gets stretched 3 times, which makes it a little bit skinnier, because if you stretch something, it kind of thins out. What you would actually get here, it would be 6x. So notice that the vertical stretch carries on with the slope function, right? It was timesing by 3 originally, and after we did the slope function, it's still timesing by 3. So the stretch factor stays with it, right? What about a vertical shift? So say we had x squared plus 1. What's that going to look like? And we're going to compare this to what we just did. So we know f of x equals x squared. The slope function will be 2x. Now, if we understand this quickly from just a sketch, we have a parabola, and along this parabola are slopes, tangent lines, right? If we shift this function up, so now we just shift it, say, up 1, what you're going to find out is that the slopes at those points are actually parallel. I'd have to continue this onwards to find the next one, because we're looking at that point. I went up to that. These tangent lines are all parallel. If I look at the first one and I extend this outwards, it's parallel with the bottom one. So this is for some value a. So what that means is that the slope function the plus 1 we can almost just ignore there, and it's still just going to be 2x. And then for horizontal shifts, we have f of x equals, say, x minus 1 squared, and then we look at, compared to x squared. Slope function of that was 2x. What's going to happen here, all right, is that if it's a horizontal shift, so we go right 1 now, and compare that to your original. The slopes are still the same at all the points, but it's just shifted over right. So that shift stays the same, but the same policy still, the same protocol still follows, where we bring that, multiply that to the coefficient in front, and drop that by a power of 1. So there it is. Hopefully that makes some sense to you. It was kind of a lot. I'm a little, something is off on the vertical shift. I know this is correct, but my picture, I might have goofed on the picture. And maybe you can find that mistake. I might have goofed. Because clearly we can see that these slope functions are not the same. I mean, yeah, they have the same slope, but this one should have a different starting value. So we'll go with that for now. And we'll, that's an extra credit question anyway. So good luck on that. Hope that helps you. Come to office hours if needed. All right, bye-bye.